everybody. All right. All right, so have quite a few announcements today, so let me get going. And I just realized I'm not in space as I usually am. So let me get back to some nice black hole. Here you go. That's better. All right, so lots of announcements. First of all, congratulations to everybody. You did fantastically well on midterm number 2. Class average was 87.88. So basically half of the class got A's, and that's great. It means any number of reasons. Maybe you studied harder. Maybe I've gotten softer and I made a much easier exam. Whatever the case, I hope that you're learning. I hope that you're getting something out of this class. And I'm glad. I mean, who doesn't like to get an A in a class? So congratulations to you guys. Very good. So next week, as you all know, is Thanksgiving week, and there will be no class on Thursday and Friday. It's a holiday. The campus will be closed. And since we have so many discussion sections on Thursdays and Fridays, we decided to cancel the discussion sections for the entire week. So there will be no discussion sections that week. That means you will have a homework 8, which is just for you to review the material, just for you to prepare for your final. And homework number 8 will not have a quiz. So you will never take a quiz on homework number 8. I know that a lot of you really appreciate having discussion section, being able to go over all of the problems. So what I have asked the TAs to do is to record a video explaining or going over every one of the homework problems for homework number 8. So sometime next week, before Thanksgiving, there will be a posting of a video that by your TAs that reviews all of the problems. So they will make an announcement, they'll post it online, and you'll be able to access that. But again, no discussion sections next week and no quiz for homework number 8. This Friday, so separate next announcement, this Friday only, we will have an asynchronous lecture, which means you do not have to log on to Zoom to have the lecture. I will be recording it and posting it early in the day. I have a conflict with schedule that I wasn't able to resolve. So I will not be teaching in real time. So I will be recording it, posting it on YouTube as usual, and I will send an announcement when it's ready so that you guys can watch it any time of the day that you want. I know that those of you who are here, all 72 of you who are here, I know that you like to have a more interactive class. So if you have questions as you are watching the video for Friday, feel free to send me an email. Feel free to send me your questions. I will get back to you. If the questions are, if there's few questions, I will just respond to you individually. If there's a lot of questions, maybe I'll just, I will just, record a video with the answers. So again, feel free to send me your questions. The next announcement, which I will make from here until the end of class, is that the final exam is in person. So it'll be on Wednesday, December 8th from 3 to 6 p.m. And it will be at the University Lecture Hall 1000. That's a very large classroom that holds more than 600 people. So there will be plenty of room for all 420 of you. You will need to bring a Scantron. It is the red one. It is form 289 par L. Please fill in your student ID before you come. I understand that the new student IDs don't have your student ID numbers in them. So a lot of people are showing up to exams now and not knowing their student ID. So please look it up ahead of time, fill it in ahead of time. And I will be posting a map just in case you're not so familiar with campus and you don't know where that is, it'll be nice to see you guys in person, although we will all be masked. And anyways, I will be there. Where can you get the 289 Par L Scantron? At the very least, you can get it at the bookstore on campus. There may be other places. So if you guys know of other places where they're cheaper or whatever, you know, just make sure, feel free to post it on the GroupMe and Discord so that everybody knows about it. All right, any other questions? Yeah, oh yeah, that's right. The ASUCR building on the second floor of the hub has free Scantrons and Blue Books. That's right. So I think, Bryant, you had told me that before. Thank you for reminding me. So I will make an announcement so that people remember. Will there be a study guide to, sort of, will there be a study guide for the final? So I hope you noticed that the questions for this exam, for the one that we just had, were basically one-on-one questions from the homework. I literally pulled up the homework and then I saw homework number 4, question 1. Okay, what can I ask that is related to that? And then I wrote the question accordingly. So I will be doing the same with the final. And the majority of the final will be focused on the next lecture. So lectures 18 through 27, I think so, through the end. And then I will ask a few questions from the rest of the quarter, but I will only focus on like the most important things that I hope that you remember. So yeah, I mean, I may even hold an in-person review session if people are interested. But I'll let you know about that. Yeah, that's right. So are you going to be able to see what you got wrong? So I set it up so that after this class, so after 5 p.m., you will be able to go on iLearn and look at midterm 2 and 1. I need to set up midterm 1 again so that you can go and see. It's a little tricky how to see what you got wrong, because you have to go and pretend that you're going to take it again. So it's like you have to do begin or something. And yeah, so I explained a few lectures ago how to do it, but I don't remember off the top of my head. So try it. If it doesn't work, you know, maybe I'll post an announcement about how to do it. So, okay. How many questions will the final be? I think it'll be, so, okay, so when we teach this class in person, it's always been 100 questions. The questions are a little easier because, you know, I don't get to do the multiple answer. I don't get to do the ordering questions. So in a sense, they're a little more straightforward. So it might be about 100 questions, but honestly, I haven't really thought about it. So you will have 3 hours to answer. So you have plenty of time. So I think 100 is better, because then if you miss one, you're only missing 1 point instead of missing 2, right? If it's only 50. So yeah, I'll let you know. What else? Yeah, okay. I think that's all the questions. Very good. So today we get to finish black holes. Starting on Friday, we'll start to talk about galaxies, then galaxy collisions, and then finally the Big Bang. So let's finish with black holes. We talked until last class, we talked about things that we know for sure about black holes, things that we have observed. I told you about some very exciting new discoveries about black holes. And now we're going to turn a little bit into the things that seem a little more like fiction. Some of them are fiction, and some of them are actually true. So I like to take the film Interstellar, which came out about 9 years ago, because it provides a good opportunity to discuss, you know, interesting things that happen in the vicinity of black holes that are actually true. So this is a special film because it was the advisor to this film is someone who is a scientist and got the Nobel Prize um, a few years ago. So it's actually based on science, even though of course it's dramatized, and I don't want to give away the end of the film, but the end of the film is totally like fiction. It's not based on science. But anyways, let me just show you a little clip about this film Interstellar, and then we'll talk about a few things about the film.
Interstellar is a visual masterpiece, but the most spectacular aspect of the movie is that those jaw-dropping shots of black holes and wormholes are the most realistic depictions of these phenomena man has ever created. Thanks to a $200 million budget only a proven blockbuster filmmaker can command, director Christopher Nolan's team had the resources to create impeccably detailed computer-generated simulations of space-time events that had previously only existed in highly complex equations. To achieve this task, Nolan's visual effects director Paul Franklin used the mathematical genius of leading astrophysicist Kip Thorne to generate algorithms that guided the effects software. In fact, it was the astrophysicist himself who conceptualized the film, along with producer Linda Obst, who Thorne worked with on 1997's Contact. Thorne's passionate about explaining the mind-bending ideas of relativity to the general public, and was thrilled when he saw the final result. The visuals are so powerful, so accurate, that Thorne's planning on publishing 2 academic journal articles based on the computer renderings of a black hole used in the film, which led to a new scientific discovery. That light temporarily trapped around the black hole produced an unexpectedly complex fingerprint pattern and a glowing accretion disk that appeared above, below, and in front of the black hole. Quote, "I never expected that," Thorne says. "It was just amazing," end quote. No one knew exactly what a black hole would look like until they actually built one for the film. Some of the single frames in these sequences took 100 hours to render.
All right, so first of all, first thing about this film is that they try to make it as accurate as possible. And I love the fact that that it was the film industry that was, I guess they put in the money to be able to run the computers and to put in the simulations to actually see what a black hole would look like if you were close to it. And so now it's become like you Google black hole and this is the picture that comes up, right? Like it's just commonplace. Everybody thinks of a black hole as looking this way. But 10 years ago, right before this film, we hadn't really thought about it. We hadn't thought about the fact that the gravitational lensing that we discussed in class would cause this pattern, so that instead of looking sort of like Saturn, you know, like with a sphere, a black sphere, and then a disk around it, it actually looks this complex lensed pattern. Anyways, let me tell you in a nutshell what the movie is about in case you haven't seen it. And again, I'm not going to spoil the end in case you want to see it. But the premise of the movie is that things are pretty bleak on Earth. We're running out of food. Everything is dusty. The crops are just not there. And so humans desperately need to find a different place to live. And somehow they managed to send an expedition of people to find a new planet, an exoplanet, where they might be able to move humanity to. And so they go through what is called a wormhole, and we'll talk about that at the end of this lecture. They go through a wormhole which allows them to cover a large amount of space in a very short amount of time. And they come out of on the other side of this black hole, which is a supermassive black hole with 100 million solar masses that they call Gargantua. And so this supermassive black hole has 7 planets going around it. Is it possible to have planets around a black hole? The answer is yes. But the conditions would have to be very specific, right? So it is a long shot, but then it's a movie, right? So, okay, so you have 7 planets, and they have to decide which of those 7 planets humans would be most likely to be able to survive. And so the first one, so they have to explore them, but they have a limited amount of time to do this. And the first one that they decide to explore is what they call Miller's Planet. Miller's Planet is very close to the supermassive black hole, and extremely close, right? And when they go there, they found a couple of things. One, that it is a world that is completely covered with water. Is this fact or fiction, right? Well, we know now that there are worlds like Kepler 22b that are completely covered by some liquid. We don't know if it's water, but given the density that the planets have, the most likely thing that is covering the entire planet is just liquid. So they find one of these planets, and Miller's Planet, and it turns out it is not a place where they can go. I mean, at first they're excited because there's water, but then it turns out it has this gigantic waves. Like here, you see like this gigantic mountain. So it makes it impossible to live there because the wave comes one way and then it goes the other one. So very quickly, I mean, this has a little less to do with black holes, but it has to do everything with gravity, right? So the issue is that the planet is so close to the supermassive black hole that, remember the tides on Earth, you know, where the moon is pulling on one side of the Earth harder than it's pulling on the other side. In the same way, Gargantua, the supermassive black hole, would be pulling, and imagine, and this is a planet that is all covered with water. So the tides would be enormous. I think one of the questions in your homework that I gave you is if the moon were more massive, or I think it was on the exam, if the moon were more massive or if it were closer to Earth, I forget which one I asked, would the tides be larger? And the answer is yes, they would be much larger. And so imagine now you have a supermassive black hole giving like enormous tides on this exoplanet, Miller's Planet, which is covered with water. And as the planet sort of tilts back and forth, and this is again because of tidal forces, then the water that makes the huge wave will move back and forth, and then it makes it completely impossible to live there because, you know, every time that the high tide goes through wherever you are, it's just going to look like an enormous mountain, and so you can't live there. All right, this is the part where I wanted to get to. They go there, so they have a friend, they have a crew member whose name is Romilly. And he's in the bigger spaceship, which is called Endurance. There's a smaller group that goes into Miller's Planet. They explore it, they realize it's not any good. So Cooper and Amelia are in in Miller's Planet. And then they go back to Endurance. So the points I want to make is Endurance is a spaceship where Romilly is, and it's far away from the black hole. It is in a place where space would be a lot flatter. It wouldn't be so curved. Cooper and Amelia go into Miller's Planet, which is much, much closer to the event horizon. And so what happens? How is life, how is the universe different in a place where space-time is not very warped, it's more flat, as compared to a place where space-time is incredibly sharply curved? Not just space, but also time. So let me play just a little bit of from a clip from the movie, and then you can see that. Oh, actually, I need to pause my recording. All right, sorry people who are watching the video, and thanks to Rosalina for letting me know that I wasn't recording. Okay, for people who are watching the video, if you were to rent an office in a skyscraper and you wanted to remain a bit younger, you would choose the ground floor because, and this is just for the sake of the video, because Einstein's theory of general relativity tells us that time runs more slowly when gravity is stronger. And even though it's a very small difference, gravity is just a tiny bit more strong or stronger, sorry, on the surface of Earth than it is high up, either in space or on a mountain. So thank you for letting me know. All right, so there were a couple of questions that I wanted to get to. So again, the difference between a mountain or a penthouse and the surface of Earth is tiny. So the reason the clock tower at UCR is often off is not because of gravitational time dilation. The person who is experiencing more gravity is the one who's going to age more slowly. So the person who is experiencing more gravity will remain younger. That's why when Amelia and Cooper go back to, far away from the gravitational field, that's why they're younger. And the other guy whose time went, at a more normal rate, if you will, not worked, he ages a lot more, and that's why he's older. Somebody was asking also, would people be able to survive in those planets around the supermassive black hole, given that there's no fusion, right? Like in the sun, is there heat? The heat would not come from the supermassive black hole. The heat would come from the accretion disk around the supermassive black hole. And it would have to be just right, because if it's too hot, then it fries the planets, right? So it has to be not a very big accretion disk. It needs to be just a little bit of stuff going into the supermassive black hole, just enough that the accretion disk is hot enough to warm the planets. So good questions. Very good. So, all right, so what would Romilly, right? Romilly is the guy who is far away from the black hole. So let's say you jump into the black hole and he watches you. What would he see? So what he would see is that as you approach the supermassive black hole, sorry, am I recording? Yes, I'm recording. Okay. So as you approach the black hole, you would start to move more and more slowly. Why? Because gravitational time dilation would get stronger and stronger as you get close to the event horizon. And in fact, time would be so slow that in principle, it would stop before you cross the event horizon. So this is something from a Hubble website.
1, 2, 3, 4, 5,
Throwing a
6,
clock into the black
7,
hole,
8,
and then you're watching
9, 10,
what it looks
11,
like.
12, 13, 14, 15,
everything slows down, right? Like time as it was ticking, and it also gets kind of deformed because that's because space is also getting warped, and it just slows down. Even the voice, even the sound waves slow down until it just stops. Do you stop? Like if you're the one who's jumping, are you going to stop? No, you actually do go into the black hole. Although there is some debate about that, right? But we're not going to cover that. I mean, essentially gravity is pulling you and you go in, but the person who's watching you, they don't even see this. Do they see you like you just stop and you don't move? Well, no, because you're also getting redder. The image of you that is going to Romilly starts to change in wavelength, right? It starts to go to longer and longer wavelengths. And this is also caused because of gravity. So you become you become red, and then you become infrared, and then radio, and then eventually Romilly is not going to be able to see you anymore because, you know, his eyes cannot detect radio waves, and your wavelength is going to stretch more and more. This is what is called gravitational redshift. So we talked about gravitational time dilation, where time goes slower in a large gravitational field. Gravitational redshift is when the wavelength of light gets stretched, it gets elongated, it gets made bigger when it experiences a strong gravity. So again, going back to Einstein, Einstein's theory of general relativity tells us that light is shifted toward the red, right? The wavelength is stretched and made longer in strong gravitational fields. The stronger the gravity, the greater the shift toward red and longer wavelengths. So that's called gravitational redshift. So even the sun, right? It emits some light, and as the light is coming out of this gravitational field, it gets just so slightly stretched. It's so small with the sun that you can't really see it. But with supermassive black holes, we actually observe this. So you have a supermassive black hole that has an accretion disk around it, and it's emitting light, not the black hole, but the accretion disk. And that accretion disk is experiencing very strong gravity. So as it emits light, the light gets redshifted as it travels out. You can think of it as light losing some energy because it has to overcome this enormous gravitational field. And so you know that light that has lower energy, lower energy has also longer wavelengths. So, you know, let's say that the accretion disk around the black hole is emitting visible light, and as it travels out, it gets stretched to infrared and then radio. So that's why if you jump into a black hole and somebody watches you, you're going to slow down as you get closer to the event horizon, but also your light is going to look redder and redder, you know, longer and longer wavelengths. All right, so finally, we get to the last thing I'm going to cover regarding black holes, which is, what about time travel? We see this in every kind of movie, and Interstellar is a great example of this. So here we go.
But what about wormholes? They've never been seen, but Einstein's theory of general relativity mathematically predicts their existence. Imagine for a moment if there was a way to open a hole in the fabric of space-time in a way that's curved, so that you could take a shortcut from one place to another. If this was possible, you might not need a ship capable of light-speed travel. Hopping through a wormhole would be incredibly difficult, but no scientists have ruled out the possibility. To show you how this would work, imagine the universe as a two-dimensional sheet. Make two holes at the end of the sheet, and then bend the sheet so that the two holes are aligned. And then stitch the two ends of the holes together, and you get a wormhole. It sounds more like science fiction, but objects like our sun and the Earth already warp and distort.
All right, we'll continue with the video in a minute. So I love your questions, and I'm so tempted to answer them, but let me get through this, and I will get back to the questions. So the whole idea is, if space and time can be warped, which we know it can, then would it be possible for space and time to be warped in a way that you could connect two places, and essentially travel faster than the speed of light? It's not that you're traveling faster than the speed of light, it's just that you're taking a shortcut. And, you know, people call that wormholes. Now, this is speculation, right? So let me try to give you a sense of why this is speculation and not fact, not science. So let me try to give you a very, very basic introduction to this. There's a lot to this, and there's a lot of videos out there. If you Google wormholes, you'll find a lot of them. But let me just try to give you a intuitive way to explain this. So just like there are black holes, there is also a theoretical object called a white hole, which would be exactly the opposite of a black hole. So where does this idea come from? From the equations of general relativity. So the mathematical solutions of general relativity predict that there is this object, white holes. So a white hole is exactly the opposite of a black hole. It is a region of space-time, I didn't write time, but it's a region of space-time into which nothing can fall. So it can only spit things out. Now, the problem with this mathematical concept is that it requires that time flow backwards. And as far as we know, time always goes forward, right? It's today, then it is tomorrow, then it is the day after tomorrow. Like, it's never like you wake up and it's yesterday. We've never experienced it going backwards. But, you know, when Einstein solved his equations of general relativity, one of the answers was a black hole. And he said, that's not possible. It's too weird. I don't think it exists. And then, you know, decades later, they actually found them. So white holes is another solution. And we're all saying, that's too weird. I don't think they exist. But who knows? Maybe someday we will be able to find them. Part of the reason why we're skeptical that they exist is because whereas a black hole, you can't see it because it doesn't emit any light, white holes would be emitting all kinds of light. So then they would be easy to see. So why haven't we seen them? But who knows? I am not going to tell you that this is not possible, but just so you know, this is speculation at this point because we have zero evidence that they exist. Okay, so what about white holes? How is that connected to wormholes? All right, so you have a black hole, and this answers a couple of the questions that I got. If you fall into a black hole, presumably in a matter of a fraction of a second or maybe seconds, you would hit the singularity, you would be crushed to nothingness, and you would become one with the singularity. However, if a black hole is rotating, which that's what I have here, a simulation of a black hole that is rotating, and the stuff around it represents the actual space being dragged around the black hole. Because remember, there's gravitational waves. Space is actually something it's kind of a thing, right? It's not nothingness. And it can be deformed and it can be dragged around. So scientists think that if you were to fall into a black hole that is rotating, it may be possible to fall into it, go through the event horizon and not hit the singularity. Is it true? I don't know. We don't know. It is speculation. So general relativity says that a rotating black hole, one of these where you might not hit the singularity, could possibly be connected to a white hole, one of these things that only spits things out. So it may be that if you go through a black hole that is rotating, you might bypass the singularity and come out on the other side through a white hole. And so in that sense, it may be that a black hole can connect another part of the universe through a wormhole, you know, with a black hole with a white hole. All right. So here we go.
Look like in 2D. Our universe is like a big flat sheet. Bent in just the right way, wormholes could connect two very, very distant spots with a short bridge that you could cross almost instantaneously, enabling you to travel the universe even faster than the speed of light. So, where can we find a wormhole? Presently, only on paper. General relativity says they might be possible, but that doesn't mean they have to exist. General relativity is a mathematical theory. It's a set of equations that have many possible answers, but not all maths describes reality. But they are theoretically possible, and there are different kinds. The first kind of wormholes to be theorized were Einstein-Rosen bridges. They describe every black hole as a sort of portal to an infinite parallel universe. Let's try to picture them in 2D again. Empty space-time is flat, but curved by objects on it. If we compress that object, space-time gets more curved around it. Eventually, space-time becomes so warped that it has no choice but to collapse into a black hole. A one-way barrier forms, the event horizon, which anything can enter, but nothing can escape, trapped forever at the singularity at its core. But maybe there is no singularity here. One possibility is that the other side of the event horizon looks a bit like our universe again, but mirrored upside down, where time runs backwards. In our universe, things fall into the black hole. In the parallel universe with backwards time, the mirror black hole is spewing things out a bit like a Big Bang. This is called a white hole. Unfortunately, Einstein-Rosen bridges can't actually be crossed. It takes an infinite amount of time to cross over to the opposite universe, and they crimp shut in the middle. If you go into a black hole, you won't become the stuff coming out of the white hole. You'll only become dead. So, to travel the cosmos in the blink of an eye, humans need a different kind of wormhole.
All right, there's a lot of different types of wormholes, and again, you can Google it and you can find all kinds of things about it. So, but this was the idea of the white hole connected with the black hole. And again, the one with Gargantua in the movie, it's a different type of wormhole that could potentially be traveled through. There's a problem, one more problem, right? Besides all the ones that I've given. Wormholes are short-lived. The gravity of a black hole would cause them to collapse almost as soon as they form, right? And this is a quote from Kip Thorne, who's, you know, the guy who got the Nobel Prize and who was the advisor for the movie. If you don't have something that somehow threads through them, that somehow keeps them open, then the walls will collapse so fast that nothing can go through them. But, you know, this never stops people from trying to solve the problem, because of course, space travel and time travel is such a cool thing that we all want it to be true, right? We all want it to work. So there are some physicists in different places around the world who are working on this. They're trying to figure out, if a wormhole exists, how could we keep it open? And what they say is that you would need some sort of a pressure, some sort of a negative energy to create anti-gravity to keep them open. This idea of anti-gravity and this weird kind of mass that would have these characteristics became a little popular in the last year, I think, when if you guys saw that movie Tenet. And if not, I recommend you watch it just for the sake of looking at this anti-gravity thing or negative energy thing. So I have a quick video, just the rest of the video that I was showing that talks a little bit about that. So here we go.
Space-time. In order for a wormhole to stay open and not collapse, you would need exotic matter that had negative energy or negative mass that would act like a sort of anti-gravity. To put this into perspective, if the Earth had negative mass and you let go of a ball standing on the surface, it would accelerate up into the sky, and to hit a negative mass tennis ball, you would swing your racket away from the ball. However, this exotic matter isn't known to exist. The problem with the theory of wormholes is that we'd need more negative energy than the rules of physics allow. To give you an idea of how much, we'd need the energy the Sun produces over 100 million years to open a wormhole the size of a grapefruit. and no one knows how even the most advanced civilization
that got cut. Nobody knows how even the most advanced civilization could harness that type of energy. So I don't mean to leave you on a low note. You know, we don't know. There's so many things that we continue to discover. Again, this is speculation at this time, but as one of the videos said, nobody has said for sure that this couldn't happen, that we couldn't travel through space and time. So it's a lot of things that we would have to overcome. Tidal forces, right? Like how you get ripped apart as you fall into a black hole. Time reversal, is there any of this going backwards in time, or the negative energy? There's so many things that would be a problem. But again, we don't know, and maybe someday we will figure it out. So I will leave it there. Thank you for coming. And again, on Friday, the class will be asynchronous. I will be sending an email to let you know that the class has been posted. So I'll answer a couple of questions, and I'll see you guys next week.